Let's dive right into this explainer and tackle what I think is one of the most fundamental yet absolutely fascinating questions in modern robotics. How exactly do a robot's base motors, which are firmly anchored to the floor, know exactly where its gripping sensors are out there in space? It sounds simple enough, but the math making this possible is literally the bedrock of automation, computer graphics, and physics.
We've got a really fantastic roadmap lined up. We're going to start with the core robotic problem, look at 2D transformations, learn the homogeneous trick, figure out how to chain matrices, scale it all the way up to 3D, and then wrap up with some foundational takeaways.
All right, Section 1, the robotic problem, kinematics and control. Let's step out of the textbook and right into the physical world.
I love this quote. Applying coordinate transformations to a robotic arm is one of the best ways to understand how these matrices work in the real world. And it's so true, right? Staring at grids of numbers can get a bit dry, for sure. But the second you realize those numbers represent the physical, twisting steel of a machine, man, the math just instantly clicks. So, imagine a simple robot arm with two links just sliding around on a flat table. To make this thing move perfectly, its controller has to translate coordinates between totally different reference points, or what we call frames. First, we have frame 0, that's our base frame, bolted to the ground. Then frame 1, the joint frame, right at the first moving joint. And finally, frame 2, the end effector frame, which sits all the way out at the gripper tip. Now here's the puzzle. If that gripper grabs an object, it only knows where that object is relative to itself. But the motors doing all the heavy lifting, they're way back at the base. They need to know where that object is relative to the floor to actually move the arm correctly.
Which brings us to Section 2, 2D coordinate transformations. Let's look at the math for flat surfaces. To bridge that physical gap between the base and the gripper, we need some mathematical tools. Say a robot joint just spins in place without reaching forward. For that, we use a 2x2 pure rotation matrix. Basically, if you rotate a frame counterclockwise by an angle, let's call it theta, you can map a point right back to the original frame using this neat little grid of cosines and sines. It is a beautiful piece of math, but honestly, it only solves half of our physical problem.
Moving on to Section 3, the homogeneous transformation trick, where we add a dimension.
Why do we need a trick? Well, because robots don't just spin in place, do they? They reach, they shift, they extend. Look at the contrast here. Pure rotation only handles spinning. But to move along the actual physical arm, we have to combine rotation with translation, meaning shifting or displacing in space. And to do both at the exact same time, that little 2x2 matrix just isn't going to cut it. We have to level up to a 3x3 matrix.
And here is where the magic happens. It's a mathematical hack called homogeneous coordinates. We literally just invent a dummy dimension. We take the number 1 and slap it right on the bottom of our coordinate vector. By forcing this extra dimension into our math, we completely unlock the ability to bundle twisting and reaching into one single elegant matrix multiplication. It's a total game changer.
See how beautifully this all fits together? Up in the top left, we drop in our trusty 2x2 rotation matrix with the sines and cosines. Over on the far right, we plug in our actual physical translation distances, dx and dy. And down along the bottom, there's our dummy row, 0, 0, and 1. Bam! We've built our homogeneous transformation matrix, and it can handle literally anything a 2D robot joint throws its way.
Okay, Section 4, chaining matrices together, or linking the joints.
Let's take those awesome 3x3 matrices and apply them back to our arm. We systematically set up a matrix for every single piece of the robot, moving link by link. Step 1, we map the base to joint 1. This joint sits at the origin, so it rotates by an angle, theta 1, but its translation is just 0. Step 2, we map joint 1 to the end effector. This frame is pushed out along the length of the arm. Let's call that length L1. And it's rotated by the second joint's angle, theta 2. So now, we've got two distinct matrices for the two physical parts of our robot. Now for the real climax of the whole kinematics problem, the chain rule. If you want to find the ultimate position of the gripper tip relative to the base, you just multiply these matrices together in sequence. T10 times T21 gives you T20. It's so elegant. You are mathematically linking the physical joints together.
And here's the big payoff. If a camera out on the gripper spots a target, it only knows those coordinates relative to itself. But when the robot's brain multiplies that gripper target vector by our chained matrix T20, it translates the coordinates perfectly. Suddenly, those base motors know exactly where the target is relative to the floor, and the robot can just reach out and grab it.
Next up, Section 5, Scaling up to 3D Space for Industrial Robotics.
Here's the cool part. If you totally understood how we just chained those 2D matrices, you already have the blueprint for massive industrial robots. Real robots move in 3D space. Up, down, pitch, roll, yaw, the whole shebang. So our homogeneous matrix simply upgrades from a 3x3 to a 4x4. The logic is exactly the same. The top left 3x3 section becomes our 3D orientation, handling X, Y, and Z rotations. That right-hand column becomes the 3D position, the actual lengths of the metal links. And yep, we keep our dummy row at the bottom with a 1.
Think about a standard 6-axis industrial robot arm. You know, those massive orange or yellow ones you see building cars? The computer uses something called the Denevet-Hartenberg convention. It calculates where the tip is by just multiplying 6 of these 4x4 matrices together right in a row. Because of this continuous chain of math, it absolutely does not matter how contorted or twisted the robot gets, it never loses track of its own hand.
Finally, Section 6, Foundational Takeaways, your coding blueprint.
Let's quickly summarize these dimensions, especially for those of you looking to actually write code for this stuff. Keep this reference in mind as your blueprint. If you're coding in 2D space, you append 1 to make a 3-element vector, and you multiply it by a 3x3 matrix. Stepping up to 3D kinematics, just append a 1 to make a 4-element vector, and drive it all with a 4x4 matrix. That is exactly how you translate textbook math into functional code.
Oh, and I have to share this computationally beautiful detail that programmers absolutely love. Rotation matrices are orthogonal. In linear algebra, this means that to find the inverse of a rotation matrix, you just take its transpose, flipping the rows and columns. Why does that matter to us? Well, calculating inverses is usually really heavy lifting for a computer, but a transpose, that's basically instant. So reversing a complex robotic movement is incredibly cheap and blindingly fast for the processor.
It is truly amazing to realize that this seemingly abstract linear algebra is the invisible scaffolding driving the automated modern world. From the simplest spinning joint to a giant 6-axis factory arm, it all comes down to chaining matrices. So, as you dive into your own coding or engineering journey, how are you going to use these hidden transformations to breathe life into your next physical project?